Determine the value that makes a piecewise function continuous. So as we know, we can check for continuity at a specific point if we use the three conditions of continuity. First condition is that the function is defined at that point. Second is the limit exists at that point. And third, the limit exists at the same height as the function. And that is very useful. Those three conditions are super useful when we're trying to identify continuity at a point. However, there are some other applications of those conditions which we'll be talking about in this video. And in this video, we need to kind of take those three conditions and combine them into one general, simple, easy to state formula. So, in general, a function f of x is continuous at x equals a when the limit from the left equals the limit from the right, and both of those limits equal f of a. And this expression, if it is true, means there is no jump, means there is no infinite, and means there are no removable discontinuities. So we could think about this equation here as the intended height from the left equals the intended height from the right, and both of those equal the actual height. And again, if all three of these pieces are in fact equal, our function is continuous at a. So let's take a look at an example where we can use this simplified version of continuity. So in this example, we are being asked to find values of a, or for what values of a is this function f of x continuous at x equals 4. And we are given a piecewise function here, and we can see that this a we're trying to find is in one of our piecewise functions. So this is a variable that's not x. So our piecewise function says that ax plus 5 is going to be our function whenever we use values that are less than 4, and x squared minus x is going to be our function when our values are greater than or equal to 4. So like we've done in the past, let's just quickly sketch a number line so we can see where all the pieces fall. So our a value is 4. We can see that when x is less than 4, we are going to use the expression ax plus 5. And then when x is greater than or equal to 4, we're going to use the expression x squared minus x. Alright, so then from here we can start out with our simplified version of continuity. And that was that the limit as x approaches a from the left of f of x is equal to the limit as x approaches a to the right of f of x, which is equal to f of a. Alright, so again, we are trying to make this equation true with the facts that we are given. So we can start plugging in the pieces that we know. So we're first looking at the limit from the left, and when we approach 4 from the left, we can see that we're going to use the expression ax plus 5. So that means we're going to have the limit as x approaches 4 from the left of ax plus 5. Now that has to equal the limit from the right. And as we approach 4 from the right, we can see that we're going to be using the expression x squared minus 2. So that'll give us the limit as x approaches 4 from the right of x squared minus x. And I apologize, I did say 2 just a second ago. Alright, and then finally we are looking for f of a. And in this case, f of a is going to be f of 4. Alright, so now we can evaluate each piece of this. Both of the limits are polynomials, so we can use direct substitution. So we are plugging in 4 for x, so that's going to give us a times 4 plus 5 is equal to 4 squared minus 4, which is equal to, and then we need to figure out, alright, which expression are we plugging 4 into? And as we can see, we're going to plug it into the blue expression, because the blue expression uses 4. So this is going to be 4 squared minus 4. Alright, simplifying this some more. Let's see, we are going to get 4a plus 5 is equal to 4 squared is 16 minus 4 is 12. And then for the final piece, 4 squared is 16 minus 4 is 12. Alright, so we have managed to get two of our pieces to be the same. We can see here that 12 is equal to 12. That is a fact. So the last thing we need to figure out is how can we get this third piece to equal 12 so that they all match. And now in order to get this third piece to equal 12, we need to do what the question is asking us, which is determine a value of a. So to do that, I'm just going to take a piece of our equation. I'm just going to take this piece right here, and I'm going to set 4a plus 5 equals 12. Because again, we're trying to get 4a plus 5 to equal 12. And now we can just solve for a. So I'll subtract 5 from both sides to get 4a is equal to 7. Divide both sides by 4, so a is going to be 7/4. So therefore, in order for this particular piecewise function to be continuous at 4, our a value needs to equal 7/4. Alright, so for our next example, we want to do the same thing, except this time we're being asked for what values of k is the function f of x continuous at x equals 4, and we're given a new piecewise function. So we're going to take a similar approach here, except instead of trying to find a, now we just have a different variable k. So first thing first, I'm going to draw my number line and plot my expressions, with 4 being the a value. When x is less than 4, we were going to use the expression 3x squared minus 11x minus 4. So shade in that piece of the graph. And then when x is greater than or equal to 4, I'm going to use our second expression, kx squared minus 2x minus 1. Alright, then I'm going to start with the simplified version of the conditions of continuity, which are the limit as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x, which must equal f of a. So now we can start breaking this down and applying it to our actual function. So here we're going to have the limit as x approaches 4 from the left. And we can see that as we approach 4 from the left, we are going to want to use the expression 3x squared minus 11x minus 4. Then we want to find the limit as x approaches a from the right, and not a. We know our a, it's 4. Come on. There we go. As we approach 4 from the right, we can see we want to use our function kx squared minus 2x minus 1. And this is going to equal f of 4. Alright, so I just need to, sorry, this is bugging me. This needs to kind of be matched up and centered there. Just a little bit off center. And there we go. Sorry about that. Just, pet peeve, a little neurotic. Alright, moving on now, we can use direct substitution for our limits because they are polynomials. So this is going to give us 3 times 4 squared minus 11 times 4 minus 4. And that is going to be equal to k, that's a horrible k, k times 4 squared minus 2 times 4 minus 1. And now for f of 4, 4 belongs to our blue piece. So we're going to be plugging 4 into that function. So we're going to have k times 4 squared minus 2 times 4 minus 1. Alright, so then we can come in and simplify. So let's see, we have 3 times 4 squared minus 11 times 4 minus 4. That's going to give us 0. And that's going to equal, let's see, 4 squared is 16, so we can get 16k minus 8 minus 1, which would be minus 9. And then that's going to equal the same thing, 16k minus 9. Alright, so we do have two pieces here that are the same, but both of those pieces don't have a k value. They both have a variable in them. So that means we need to look at our third piece, which is 0. No variable there, just a number. which means we need to make sure that 16k minus 9 equals 0. So we can do that. We can do 16k minus 9, set it equal to 0, solve for k, and then boom, each of the three parts will equal 0. So we're going to get 16k is equal to 9, and k is going to be 9 over 16 as the k value which will make our function continuous at x equals 4. Alright, for our next example, we're doing the same thing. We're trying to find the values of k that make this function continuous at 2. However, there's something a little bit different about this particular piecewise function. And that difference is that now both pieces have this k value. Does that change anything we do? Absolutely not. That just kind of, sometimes scares folks. So we continue to do what we do. So again, I'm going to start out with a number line to identify which piece goes where. So when x is less than or equal to 2, I'm going to use the function kx plus 5. So let's just shade in that area there on our number line. Boop, 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 boop. And kx plus 5. And then when x is greater than 2, we're going to use the expression k minus 3x. Alright, so then we can start. So we're going to have the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, which then equals f of a. And then from here we can start filling in the different pieces. So first we're going to have the limit as x approaches 2 from the left. And as we approach 2 from the left, we can see that we're going to be using the expression kx plus 5. And then that's going to be equal to the limit as x approaches 2 from the right. And as we approach 2 from the right, we can see we're going to be using the expression k minus 3x. And then this is going to equal f of, we said our a value is 2. Alright, so now we can evaluate the limits on the functions. So the limits, direct substitution. So we're going to get k times 2 plus 5 is equal to k minus 3 times 2, which is going to be equal to, let's see, where does 2 exist? 2 exists on red. So this is going to be k times 2 plus 5. And need to go back a second. I said k, but I accidentally wrote 5 here. So let's make that quick change. Alright, so then we can start simplifying everything down. So we're going to get 2k plus 5 is equal to k minus 6, which is equal to 2k plus 5. Alright, so now the difference here, as opposed to the previous two examples, is that now each of our three pieces is an expression, and none of them are numbers. But we know each of these three pieces need to equal the same value. So we're going to have to solve for k that make all three of these pieces the same value. Well, as we can see, two of the pieces are already 2k plus 5. So in order to figure out what k is, we're going to take 2k plus 5, and we're going to set it equal to that third piece that's different, which is k minus 6. And now we just solve for k. So I'm going to subtract k from both sides to get k plus 5 equals negative 6. I'll subtract 5 from both sides to get k equals negative 11. And that, ladies and gentlemen, is the k value that will make all three of these pieces equal the same number, which will make our function continuous at x equals 2. Alright, for this example, we're going to do the same thing as before. We're trying to figure out what values of k is the function f of x continuous at x equals negative 3. This example is a little bit different because if we see here, we now have an expression that not only has two terms with the k, one of the terms has a squared. So we'll start off the same way we always do. We're going to draw the number line, and let's see, our a value is negative 3. So when x is less than 3, when x is less than -3, we're going to use the function -6x plus 12. So when x is less than -3, we'll shade in that area, and then we'll get -6x minus 12. Now when x is equal to -3, so at that spot and at that spot only, we can see we're going to be using the expression k squared minus 5k. And then finally, when x is greater than -3, we're going to be using the expression which is just 6. Woo, what a nice, easy, constant function there. All right, so now starting off with our simplified version of continuity, we know that we have the limit as x approaches a from the left of f of x has to be equal to the limit as x approaches a from the right of f of x to eliminate any jump discontinuities or infinite discontinuities. And then all that has to equal f of a, so we can eliminate removable discontinuities. Then we can come in and we can plug in our specific information from this problem. So we're going to have the limit as x approaches -3 from the left. And as we approach -3 from the left, we can see we're going to be using the expression -6x minus 12. That is going to equal the limit as x approaches -3 from the right, which, as we can see, as we approach -3 from the right, we're going to be using the expression 6. And this is all going to equal f of -3. Alright, so now we can start evaluating things. Let's see, for the first limit, we have direct substitution. So we're going to get -6 times -3 minus 12. And that's going to equal just 6. And let's see, f of -3. So if we look at our piecewise function, where does x equal -3 here, and x equals -3 right on our blue point. So we're going to plug the -3 in for x into my k squared minus 5k. But here's the issue, there's no x to plug that -3 into, so what do? Well, there is no x to plug the -3 into, so we just write what we have. We have the x squared minus 5k. And then we can continue simplifying here. -6 times -3 is 18. 18 minus 12 is 6, which equals 6, which equals k squared minus 5k. Alright, so we know that 2 out of the 3 components equal 6. We now just need k squared minus 5k to equal 6, so that's where we'll start. So we're going to set 6 equal to k squared minus 5k. And here we have a quadratic equation, which means we need to set it equal to 0. So I can subtract 6 from both sides, because 0 is equal to k squared minus 5k minus 6. And I've run out of room, so I'll continue up over here. Then we can factor this. This factors into k minus 6 times k plus 1. And then we can set each of these factors equal to 0 using the zero product property. And this is going to give us answers of k equals 6 and k equals -1. Now the question is, are we allowed to have two k values that make this function continuous? And yes, absolutely. Both of these k values will make our expression k squared minus 5 have an output of 6. So therefore it would meet the other two functions. So both of these k values are correct answers, and it even gives a hint of that in the question by having the optional for what value values. So therefore we can say f of x is continuous at x equals -3 when k is equal to -1 or k is equal to 6. And there we have it, finding the k values that make the function continuous.